Ngalakin kadijan nyunga boja.
Okay, good morning everyone. So let's start our tutorial 3. And this tutorial is the very last part of the chapter 1, the random variable. And the questions covered in the tutorial 3 are related to the vector of random variables plus some estimators like the MAP or ML, minimum mean square error estimator, or even the linear MMSE estimators. And I think in the session today, we have 7 questions in total. But to say the truth, some questions are pretty hard, and I think it will take a long time to go through them. And I will try my best to go through as many as possible within these 2 hours. But definitely, we are not able to finish all the questions. And if the questions cannot be finished, so after this session, I'm going to put the selected answers plus the solutions on LMS. You can just go through them by yourself after class. And out of these 7 questions, I want to skip the question number 6 because this question is really simple. And also in our week 3, I think lecture video A, I have gone through this in the lecture when we discuss the relevant formulas. So today in this discussion of the tutorial 3, I'm not going to do this question. So please do that by yourself, okay? Of course, in the solution, you can see all details. And in the remaining 6 questions, okay, I want to just give you a highlight. So question number 1 and question number 7 are pretty hard. Sorry to say, it should be very, very difficult. And I don't think our class test will be having such difficult questions. But for your understanding, I still have to go through them, and it will take a long time. And remaining questions, so question 2, 3, 4, 5 should be okay. So let's just see how many questions we can finish. Okay. Okay, let's start from the question number 1. So on your side, please have your draft the paper and pen ready because we are going to go through this question together, and it involves some long calculation. Okay. So question number 1: a point x equal to x, y, and z. So this bold-faced font x means a vector actually. So x equal to x, y, z. The x, y, z on the right-hand side are just 3 random variables in this so-called vector or collection. So this is the question related to a vector of random variable. And another special point is this point x is selected at random inside of a unit ball in a 3-dimensional space. In other words, the x, y, z on the right-hand side are actually the coordinate of a point in the ball in this 3-dimensional space. Okay, so this is condition. So the question A, the condition is so simple, just one sentence, right? A is asking you to determine the marginal joint PDF of x and y. Okay, let's just try this out. So question 1, part A. The question is asking you to determine the marginal PDF. So for PDF, is F. The marginal means we are not going to cover all the random variables. So we're going to pick up some of them. So in this question, it's just about x and y, these 2 random variables. Hold on. So everyone, just could you please give me a response? Because in my earphone, I hear something else. Can you hear me, everyone, on Microsoft Teams? Could you let me know, please? Is there anything wrong? So you can see the share screen, right? So everyone, just let me know because something different from my side. Okay, fine, thank you. So let's just keep going. Thank you very much. Where are we? Okay, we want to determine the marginal PDF of the x and the y. Of course, in the function, we are going to use lower x and lower y as the parameter. And for this question, because you have 3 random variables inside. So the margin of xy, based on the formula we introduced, is actually equal to integration, because we want to remove the z effect, right? So we give the joint PDF of x, y, and z as the parameter of the the integration. And then because we want to remove the z, we put z here. Of course, for this continuous case, the z should start from negative infinity to positive infinity. Okay, this is formula. But for calculating this marginal PDF, we need to use the joint PDF of x, y, and z. But in this question, the condition didn't specify what is the joint PDF of x, y, and z. That's the first question. Sorry, sorry, my fault. So our first issue is how to solve the joint PDF of the x, y, z. These three random variables. But what conditions do we have? So we know, first of all, in a three-dimensional space, we get a ball. And this ball is a unit size ball. So unit size means the ball function is x, I think that's too big. So give me just 1 second. X squared plus y squared plus z squared equal to 1. So this is the mathematical function for the ball in a three-dimensional space, right? Sorry. This one normally should be the radius square, but because we got the unit size of ball, so r equal to 1. And then on the right hand side, we just got single number 1 here. Okay, so we leave it alone. But after knowing this one, anything else we know? We just know within this unit ball, this random variable or random point x is the collection of the x, y, z. These three random variables. Of course, because this point is within this unit ball, so this x, y, z combination must be within the ball. Okay, let's quickly draw this ball. Let's say we have x, we have the y, we have z here. So everyone, I want to apologize. I'm not good at drawing. Okay, so I'm trying my best to draw the 3D ball, but I'm not sure if it's clear enough. Okay, this is XY circle, and this is our. Let's try to draw it. The YZ circle. So I think our ball should be like. Okay, terribly. Okay. This is a ball in a three-dimensional space. Okay, and if a point defined by x value, y value, z value is within the ball, for example, that point is given here. Okay, sorry. This point is x, y, and z. Okay, so if this point not only on the surface of the ball, is also possible inside of the ball. So if this point is within the ball, so this point must satisfy the condition that x squared plus y squared plus z squared is smaller or equal to 1. So this is on the surface of the ball. This is the surface plus the inside of the ball, the whole body. Okay, ball, body. So this in here, because the point must be within the ball, so the probability that x1 plus y squared plus z squared smaller or equal to 1 must equal to 1. So 100% sure. And how about the point out of this ball? We don't care. The probability is 0. We don't worry about them. Okay? So in other words, such probability is equal to 1 means the point must be within the ball. But in this ball, in the whole body of the ball, there are millions of single points. For each single point, what is the probability that the point fall into that point? X, Y, Z fall into that point. That is our PDF equals 1 over the volume of the ball. Why do we do this one? Because the volume of the ball includes all the possible points within the body of the ball. That means the volume of ball is the summation of the millions small points. The 1 over that indicates what is the probability that this x, y, z fall into a single point within the ball. So regarding the volume of ball, so you have known that the formula is simple. That's equal to, I think, 4 over 3 pi r cubic. I think this is right. Yeah, should be fine. And because the radius of ball is 1, so this r cubic is equal to 1. So result is 4 over 3 pi. So in other words, for our joint PDF for these 3 runner balls, it should be equal to 3 over 4 pi. Okay, this part question is a bit tricky. Not so important, but just knowing it. Okay. Now we have already got our joint PDF of x, y, z, these 3 random variables. And then we are going to go back to our equation and use this formula to determine the joint PDF of x and y. I mean the marginal PDF, okay? So this gives us fxy equals integration, and we just copy down 3 over 4 pi inside of the integration, and then dz, because you want to remove the z. But regarding the boundaries of the integration, be very careful. It's not from -1 to 1. If you do so, the result is wrong, because if you do so, first of all, you got a constant number, not a function of x and y. This is the first point that makes sense. The second point is you are defining the hard boundary of z between -1 to 1 without considering the varying value of the x and y. Okay, but how to define the boundary of the integration? We go back to our plotting. So for a random value of the x and the y, for example, x here, y here. So we define a single point on the xy plane here. And then from this xy point, we go up and down and go to the intersecting point with the surface of ball. That is the start and the end points of the integration. But mathematically, how to represent these 2 points on the surface of the ball? Because we have the function of the ball surface. As I mentioned, we are assuming the x and y to be fixed temporarily. So the z value, so I don't have space over there, so I just keep writing on the right of the graph, right? You know the x squared plus y squared plus z squared equal to 1. Now we want to determine the boundary of the integration. X and y are temporarily fixed within this integration. So z is a problem. So we just need to move the x squared, y squared thing to the right-hand side. So that z squared equal to 1 minus x squared minus y squared. But we want to know z value, right? The z value is positive or negative square root 1 minus x squared minus y squared. So this pair of values should be the boundaries of the z value. So in other words, in our integration, the lower boundary should be the negative half z value, which is negative square root 1 minus x squared minus y squared. Too small. And the top boundary of the integration is positive 1 minus x squared plus minus y squared. Okay, so sorry, the space is too small. Okay, this is the formula used to calculate the marginal PDF of the x and the y. My dear students, could you please mute your microphone on your side on Microsoft Teams? Thank you very much. Inside of the integration, so we got one constant, so move it out. And then the remaining thing is just the upper boundary minus the lower boundary. This is bracket minus 1 minus x squared plus y squared. Sorry for the message writing. So result is 3 over 4 pi, and then 2 by square root 1 minus x squared minus y squared. So cancel. The result is 3 square root 1 minus x squared minus y squared, then 2 pi. Then finish. Okay, so this is part A. Let me double check. I think this is right. Oh, good. Okay, everyone, does this make sense? Any questions? Sorry, just 1 second. I think I'm coughing. Okay, let's keep going. Second part is pretty hard. Okay, so in the part B of question number 1, please find the marginal PDF of x. Okay, question number 1, part B. We want to determine what is f(x(x) z. So in other words, we want to remove both of the y and z from our joint PDF. Simple thing, right? So we just need to do the double integration, 1 for y, 1 for z. So let's just make this up. So double integration, and inside of double integration, we just got the joint PDF of the x, y, z. But we want to remove the effect of y and z, and then the remaining thing will be the so-called x term. Okay. How to do that? So this part should be fine because we have already known the joint PDF. So we just copy the whole thing into the integration. So how much is that? Is 3 over 4 pi. 3 over 4 pi and d what? dz. And then let's do 2 steps to finish this double integration. Okay. The first step is to focus on, maybe we pick up there first. It's integration. So how about the 3 over 4 pi is constant? We move it out of the whole thing. Okay, 3 over 4 pi is given here, and then dz. This is the first step, and the second step is another integration for the y. So let's focus on this part first. Of course, so far this integration it just kind of makes sense in terms of mathematical ways, but regarding this particular question, the boundary of the z is still the issue. You can't start from negative infinity to positive infinity for this unit size ball. So here, we need to change the boundary to what we have discussed. So in the previous questions, we have mentioned that should be negative square root 1 minus x squared minus y squared, because you are focusing on the z temporary, right? So same issue. And on the top, so the upper boundary is positive 1 minus x squared plus, sorry, again, minus y squared. Okay, this whole thing. And keep going, which is really long one. And then negative infinity to positive infinity dy doesn't change. So after solving that internal integration, we got that result from the part A, which is, I think, 2 by square root 1 minus x squared plus y squared minus y squared. Okay, this thing. The 2 can be moved out. So we just remove this 2 and cancel it with this number 4. And then we have 2 left at front. Okay, so far everything looks fine. But from this moment on, you got in trouble. Okay, so first of all, regarding this integration with respect to dy, again, you can't do this thing. Okay, so what will be used here? But in this integration, we don't have the z term anymore. So this is just really just about y and x only. That means we can treat z to be any value temporarily, but not 1 or negative 1. Okay, so it's just any value. And then for any value of z, the xy plane at that z value should be a circle, just a circle. And then, in other words, quickly, so if this is above in the 3-dimensional, of course, so something like this, whatever. And then at a given point z, for example, I pick up z here, and then we got a small crossing section area from the ball at z. This crossing section is actually, this is x, this is y, this is z, right? Is corresponding to x and the y plane. So now I'm changing to the two-dimensional view. Okay, it's a circle. So this thing is changed to this one. Sorry. This value and this value will typically not 1 or not -1. Okay, so it depends on which z value we are using. And we are going to do the integration within the x1 plane like this one. How to solve that quickly? So here. So we need to change the boundaries. And for such boundary, we use the same way to do that. So because you focus on the dy thing, right? You focus on dy thing at a particular x value. So I'm using green pen here at a particular x value. So the boundary of the integration should be this point and this point. This is the lower boundary or start point. This is the higher boundary or the end point of the integration. So from this cycle, you should be able to determine the lower and higher points easily for the y integration. So now we just write this down. That's equal to 3 over 2 pi, and then this part remains unchanged. dy doesn't change, but the boundary should be, okay, at bottom is negative square root 1 minus x squared, and on top it should be positive 1 minus x squared. Okay, this is the next step. And for solving this integration, do some change. Okay, we want to set the a equal to 1 minus x squared. So in other words, 1 minus x squared, 1 minus x squared, 1 minus x squared will be replaced by a. So it doesn't matter because in this question here, we are doing the integration with respect to the dy, the y variable. So replacing the x by the a term, my fault, a squared equals this one. So by replacing this 1 minus x squared with a squared, it doesn't change too much things regarding y. Okay, so by doing this way, well, what you got is 3 over 2 pi, then negative a to positive a square root a squared minus y squared dy. Okay, this is what we got. Okay, next step will be the key to this problem. We have been given condition at the beginning of the question that within this unit ball, we have the x squared plus y squared plus z squared equal to 1. But in this case, we are defining the 1 minus x squared to be a squared. In other words, if you move this x squared to the right hand side, so that gives us y squared plus z squared equal to 1 minus x squared. But we are defining this one to be a squared. So we can say the a squared is actually equal to y squared plus z squared. Okay. But what does this mean? So a squared equal to y squared plus z squared. Actually, this is indicating a cycle in the yz plane or yz direction. So things will be like this. Again, the ball is given. So this is the x, y, and z. So our ball is given here. And maybe another circle is given here. Okay, our ball is given here, right? But in this case, because we focus on a squared equal to y squared plus z squared, so actually we can assume the x value is temporarily fixed because we don't worry about the x, right? And at this x position, so we are going to do so-called the intersecting crossing area. So that gives us a cycle, which is in parallel with the yz plane. So this cycle is defined by this. And what is A here, or A squared here? The A is actually the radius of this black color YZ plane cycle. Okay, so now if we draw this in the two-dimensional space, for this black color YZ cycle, it looks like this. This is Y and this Z. Its radius is A. Okay, so this whole thing what does it mean? The a squared equal to y squared plus z squared. After understand this in here, so we need to understand what we are doing, what we are calculating here. So we are doing the integration of this thing. I'm using highlighter anyway. This thing multiple dy, and the change range of the y is from negative a to positive a. So first of all, let's have a look at the dy. dy is a small y direction change, right? So y direction is given here. The small y direction change maybe just given here. So this small right segment along the y direction is the dy. dy multiple what? This thing. What is square root a squared minus y squared? We said a squared equals y squared plus z squared. So a squared minus y squared is equal to z squared. And square root a squared minus y squared is the z. Of course, in this case, it's positive only. We didn't include negative, okay? So this term is actually the height of the curve at position dy. In other words, the thing is given here. This height is z, which is equal to positive square root. So what? A squared minus y squared. So in other words, this multiplication, the square root a squared minus y squared, multiple dy is calculating the small area given in this column. And the change range of the y value is from, you can see here, from negative a to positive a. In other words, we are going to examine all these small columns one by one from the negative a up to the positive a, and adding up all these areas together one by one, following the shape of the top half circle. So again and again until you reach the very last one. So by adding up all the areas of such a small column, the final result is actually the area of the top half of this circle, the yellow area in this plotting. Okay, I want to skip the calculation because from the solution you can check the details. I just help you to understand what we are doing. Okay, so in the solution we are using the angle to do calculation, but that's small thing. You can just understand this one after I draw this curve or the half circle stuff. Okay, and that means it's right hand anyway. 3 over 2 pi doesn't change at the beginning, and the whole integration is giving us the total area of the half circle, and the radius of this half circle is a. So if you want to calculate total area of the whole circle, it's pi radius square, but we are focusing on half of that. So we just divide the total area of the big circle by 2 to get half area of that. This gives us 4 pi. Pi is cancelled, I think. Pi is cancelled, and then the result is 3a squared over 4. Okay, maybe hearing my explanation is easy, but mathematically, this part is not so simple. So shortly after this session, when you see the solutions, you can find this thing is really complicated in the mathematical calculation. Okay, but anyway, we have done the calculation for the part B. So this is our marginal, the PDF of the X random row. But because this unit ball is symmetric in the 3-dimensional space, so for the other two random variables, fy, y, and fz, z, they are all equal. Okay, they are all equal. Let me double check. I think I made a small mistake. Just give me 1 second. The idea is totally right. Just the numbers. Okay. Oops, sorry. I think I made a small mistake here. So that's my idea is totally right. But because let's just start from this part. Okay. Sorry for that. Small thing here. So this part is totally right, and 3 over 2 pi remains unchanged. temporarily forgot this thing. Okay, and then so for this integration, of course, it's calculating the half area of the circle here. That's totally right. And after we finish calculation, we have one variable inside because the inside of this square root a square minus y square gave us the height of z. And then dy, y is starting from negative a to a. That all good. And this gives us 3 over 2 pi, doesn't change. And the remaining thing should be half of the pi a square. And then pi and pi cancelled is 3a square over the 4. But regarding this a, we need one more explanation. So a is actually equal to 3 over 4, 1 minus x squared. Why we have to use x? First of all, this is a function of x. First of all. Secondly, this a is our assumption because we define the a is equal to, where is it? Okay, we define the a squared equal to 1 minus the x squared. So we can't use this assumption as the parameter. So once we got the a squared in the final result, the a squared must be replaced by the original parameter x. So a squared is equal to 1 minus x squared. Okay, so this sorry for that. So only the very last step, I forgot it. Okay, for the other two marginal PDFs, so fyy must be equal to, again, because ball is symmetric in the 3-dimensional space, so we can write down the answer instantly. And for the z one is 3 over 4, 1 minus z squared. This looks much better. Okay, so I have x. Okay, now this just a result of the part B of the question. Not simple, but it can help you to understand what we are doing. Okay, it's really long one. Okay, let's move on to part C. Part C is asking what is the conditional PDF of x and y given the z. So this question, now part C of question number 1, we want to determine the conditional PDF of what? Of x and y. Of course, we have the x and y here. Based on the condition that the random variable z equal to the given value lower z. Okay, this is what we have. I think this question is much easier than the part B. By using the formula we introduced in the week 1, so we are going to use the Bayes theorem. So this conditional PDF can be interpreted to be the joint one. The joint means joint of all random variables. Okay, so x, y, z, x, y, and z divided by the marginal PDF of the condition random variable, which is f z and z. And regarding the joint PDF, we have got a value is 3 over 4 pi. And for the marginal PDF of z, so we got that from part B, which is 3 over 4, 1 minus z square. 3 over 4, 3 over 4 are cancelled. So this gives us 1 over pi, 1 minus z square. This question is so simple, okay? Good. This part is done as well. So C is done. Part D of the question is asking, so regarding the 3 random variables given in this vector, are these x, y, and z independent or not? Okay, let's just recall what we learned from lecture. So if random variables are independent between each other, there are 2 important formulas. First one, the joint CDF. So we're using the 3 random variables as example, must equal to the product of the individual CDF of each random variables. Okay, and also the joint CDF must have the similar relationships. The joint one equal to the product of the marginal PDFs for individual random variables. So I have z. Okay, if the random variables are independent of each other, so these two formulas must be true. So for this question, if the question is asking us to check if they are independent or not, so we just use maybe the second formula is very convenient. For this question, the joint PDF for this three random variable is how much? 4 over, sorry, 3 over 4 pi. Is this equal to the product of three individual marginal PDFs? Of course, result is wrong. It's not equal. Because for the fxx, it says 3 over 4, 1 minus x squared. And then for the next one is fyy is 3 over 4, 1 minus y squared. Then 3 over 4 minus 1 minus z squared. I don't need to check anything. So this must be not equal between each other. So in this case, we can say because they are not equal. So now I'm saying they are not equal. So the x and y and z are not independent. Okay. Again, I don't write the answers here. So they are not independent. So everyone, I will just pause our recording temporarily. It seems there are some issues with the Microsoft team. Let me have a quick look on that. I can't stop it. Anyway, okay, everyone. So I can't stop the recording, but please let me know if you have some issues on the Microsoft Teams. Screen disappear. So how about now, everyone? Can you see the screen? Ooh. Okay, everyone. It seems we have some technical problem with the Microsoft Teams. I'm seeing your comments or message, and many of you cannot see the screens, right? How about now? Can you see the screen now? Okay, sorry about that, everyone. So again, this is out of my control, and luckily, so this session is recorded, and if you can't see the screen before this one, so guys, how long can't you see the screen? For 5 minutes or 10 minutes or something like that? Which part did you miss? 2 or 3 minutes. Okay, luckily only 2 minutes. Sorry guys. So I can repeat this 2 minutes. So if that is 10 minutes, so I can't make it. Okay, before I start again, everyone. So I want to confirm you can see the screen right now, right? Okay, good, beautiful. Only the last equation. Okay, guys. Now, okay. So I think 2 minutes will be totally fine. Regarding part D here, we said, I just quickly repeat again. Okay. For the x and the y or z or whatever, if you have multiple random variables, if you want to judge if these random variables are independent or not, so we just need to use these two formulas. If these random variables or group of random variables are independent between each other, so the joint CDF or joint PDF must equal to the product of the marginal CDF or marginal PDF of the individual random variables. So this is the equation we introduced in lectures. For this question, we just want to check, because we want to check if the x, y, and z are independent or not. So we want to evaluate using the second formula. What is the joint PDF? And what is the product of the marginal PDF of the individual random variables? And then compare if they are the same or not. So on the left-hand side, from our analysis, we know the joint PDF is 3 over 4 pi. On the right-hand side, the product of the individual random variables marginal PDF are given like this one, this one, this one. Then we do the product of these three terms. The result is definitely not equal, because on the left-hand side, you got constant. But on the right-hand side, you got a function in terms of x and y and z. They cannot be equal. Because they are not equal, so x and y and z must be dependent between each other. Okay, this is question D. I just give you some side notes. Okay, this is everything regarding the part D. Okay, so this is the rules for independent random variables. So if these two equations can hold, the random variables are independent. But in our analysis, doesn't hold. So the random variables are not independent. Are not independent means they are dependent. Okay, so this gives us result. So x, y, and z are dependent. Of course, they are dependent because you are using the x and y and z to define a point in the ball. So the position of the point depends on both x, y, and z thing here. If x, y, and z are independent, so the position of the point is out of control. It can go anywhere in the three-dimensional space, which that makes sense. Okay, let's see part D. Oh, I know, guys, it's a long question. We spent 40 minutes on this single one, but not finished yet. Very last piece, going. Part E. So we want to determine the mean vector. Okay, when you see the mean vector, that thing must be associated with a vector of random variable. Okay, so this first thing. Second thing, we want to determine what is the covariance. Sorry for the writing. VARANC covariance matrix of this X. So actually, I should use the bold face font. I mean, this X is a vector. Okay, this is a vector. So I don't know how to just write. Yeah, this vector. Of course, this vector is equal to X, Y, and Z. So the collection of these three individual random variables. So how to do that? Okay, first of all, the mean vector of the X. So let's use the mu to denote this vector. Again, I don't know how to use the boldface font in writing, but I tell you this mu is not a value, it's a vector. Mu about this X vector is equal to the expectation. So in this concept of the mean vector, okay, of the X, Y, and Z vector. And then this expectation operator can be given to each of these three random variables. So that means EX, EY, EZ. And remaining thing should be simple, right? So that's equal to, can you recall how to calculate the expectation? So for example, if you talk about EX, this EX is actually the mean value of the X random variable, okay? If the X is continuous, of course, in this case, X is, okay? We are going to use integration and the dx. This is just framework. And inside of integration, we put the X value. This X value is corresponding to this X variable. Multiple the distribution, or in other words, the PDF of the X. And X by default generally cover the whole range of X. Okay, so this is the formula calculating the expectation. And for this question, I think the work should be pretty simple. Talking about this particular example, that's equal to -1 to 1 X. And then for this PDF of the X, we just need to go back to part B. You can see here, we got the PDF, the marginal PDF of the X itself. So it is 3/4 1 minus x squared, then dx. Sorry, I think this integration should be okay for you, and we don't have too much time left. We need to move on. So I leave the calculation to you. So here I give you the answer. Result is 0. Please do it by yourself, and you need to know how to do it. Okay. Okay. So by repeating the same procedures, you can work out the EY and EZ, the mean values of the Y and Z, these two random variables are also zeros. So in other words, the mean vector for this vector of random variable are 0, 0, 0. which is also a column vector. Okay, so this part is done. Now let's just remove all this stuff and move on to the covariance matrix of X. Can you recall what is a covariance matrix? So we are using C to denote the covariance matrix for the vector of random variable capital X. Shortly, when you check out the solutions of this tutorial, you can find sometimes we are using the K to denote the covariance matrix. Such kind of a K notation was used a long time ago, but if that textbook was from 1985 or 1987, maybe 20 years ago anyway. So the notation was the old style, but in this unit we are using new style. So in the selected answers, the notations are following the K terms, the old style. But in my full solutions, I'm using the new style, like CX or CXY or something like that. So please follow the notations used in the lecture slides. Okay, don't use K in this unit, please. Okay, CXY. CXY for this X vector of random variable should give us a 3 by 3 matrix, and there are 9 elements. So the first one is the C11, then C12, then C13, and C21, 22, 23, and 31, 32 is 33. Okay, you have 9 elements. What are these notations mean? Okay, we randomly pick up one, C21. This C21 means the covariance between two random variables. But which two? So we said in this X vector, you have X, Y, and Z. These 3 random variables. This is the first one. This is the second one. This is the third one. This is C2, 3. The 2 and 3 means I'm going to focus on second and third random variables from this vector. Of course, this means the Y and Z in this example. So we got the Y and Z. So we want to use the C23 to denote the covariance between the second and third random variables from vector, and other elements are the same. Okay, so have the same meaning. So this is what we are going to do. And if we understand this in here, so we can just rewrite this matrix as the name of the random variables. So that means CXX, CXY, CXZ, CYX, CYY, CYZ. Leave it alone, don't worry about that. And CZX, CZY, and CZZ. This in here. And okay, now it's pretty clear. And you can see, as I mentioned in the lecture, so along the diagonal direction of this matrix, these 3 elements are actually the covariance of the random variable with respect to itself. By using the formula, let's give us the expression of x minus mu x by x minus mu x. This is actually the expression of x minus mu x squares in here. This is actually the variance of x. So in other words, we keep going here, right? It's equal to sigma x squared, sigma y squared, sigma z squared. And other terms of diagonal were not affected. That also just the things here, okay? So that means we need to work out the elements along diagonal direction and also the elements of the diagonal direction. So for the elements along the diagonal direction, so they are all the variance of the random variables. Let's just pick one to work out. So what is the variance of x, for example? So the variance of x is equal to, so this is week 1 knowledge. You should be familiar with it very much, okay? It's actually equal to EX squared minus the square of the EX. But from our calculation in this step, we have already known the mean value of the X is 0. So this term is 0. In other words, the variance is just equal to the EX squared for this case. EX squared is the expectation of the X squared. Using the formula of the expectation calculation, we got the integration of whatever you have. So you got the X squared here, right? So put the X squared here. Then multiply the PDF of the X. So this is fxx dx should be from negative infinity to positive infinity. But for this question, because X is within the ball, so it's from -1 to 1. And this PDF of X, we have known that how much is 3/4. I don't copy that. 3/4 1 minus X squared to be the fxx. So by substituting this one into this integration and work out this integration, you can get a number. So I give the number is 1/5. Okay, this will be the same for the other two random variables. Okay, this is what we have done, and then along the diagonal direction, we know the values. They are all 1/5. So we write 1/5, 1/5, 1/5. Now, the only thing left is just the off-diagonal elements. So CX1, for example, we said CXY is the covariance between the X and the Y, these two, not lower Y, is the X and the Y random variable, which equals the expectation of X minus mu X by Y minus the mu Y. Okay, this is the concept of covariance. And mu X is 0, mu Y is 0. So we have done that before, okay? So this gives us the expectation of X by Y. Again, using the formula of the expectation to calculate this value. But because X and Y are all involved, so you need to use double integration. Then X by Y by the joint PDF of X and Y. So fxy xy dx dy. Again, by default, the boundary of the double integration should from negative infinity to positive infinity, negative infinity to positive infinity. But for this particular question, we should change the boundaries. Change to what? Okay, I don't have time to give you the full explanation because in the part C or part B, we have done the explanation. So here, I just give you an answer. You can refer back to know the reason of that, okay? It's negative 1 minus y squared, positive 1 minus y squared for the X. But for Y, negative 1 to 1. Okay, this will take a moment for you to do calculation. Final result, 0. You can repeat this step for all other covariance for the elements of the diagonal. So the final result is 1/5, 1/5, 1/5 for these three. For all other elements of the diagonal direction, the values are all zeros. Okay. Okay, this is everything regarding the question number 1. I believe some of you may have noticed an issue. Did you notice for this covariance between X and Y, we got a value of 0? Does this make sense? Because in the part what? Okay, in the part D of the question, we derived one important conclusion. X and Y and Z are dependent. Is this result? So X, Y, Z are dependent. And this CXY equal to 0. Are these two conclusions conflict with each other or not? So everyone, if you have some idea on this question, please type that in Microsoft Teams. I want to see, what do you think? So CXY equals 0. this from part D calculation. And also is this part E calculation. Part D is saying X, Y, Z are dependent. Are these two results conflict or not conflicting? Very nice, Karen. You just hit the point. Very good. Okay, everyone. So on Microsoft Teams, please have a look Karen's answer. They are all correct. Okay, so but have good. So Zhen Yuan Zhao, good work. You guys are really nice. Very good. Okay, let's go back to our question sheet here. Okay, here. Part D. In the part D, we are saying X, Y, Z are dependent. What does dependent mean? Dependent means these random variables have some connection between each other. So one random variable can affect the other one, vice versa. So this is dependent. But how close the relation is? So what kind of relation do they have? Is that linear relationship, second order, or third order relationship? No idea at all. But we know they have relationships, maybe higher order, maybe first order. But in the part E, in our calculation, this covariance CXY is equal to 0. This is just indicating the X and Y do not have linear relationship. In other words, they don't have first order relationship. Okay, now the idea is pretty easy. So X and Y have relationship, but the relationship cannot be linear, cannot be first order. So that means the X and the Y may have second order or third order relationships. Get that? So these two results are not conflicting between each other. And also regarding this particular question, we know this is about the ball or circle or something like that. The relationship between X and Y is definitely second order relationship. That. So we are using our calculation to prove this to be true. Okay, everyone. So this is about our question number 1. You know, we spent the whole hour on this question. Some steps are not easy to say truth. The part B are pretty challenging. And if you are not able to solve the marginal PDFs of the random variables, you will not be able to solve the remaining part. For example, you will not be able to solve this section. You will not be able to solve this one as well. So that step is important. But in the test and exam, I don't want to put such kind of hard question in the test because it doesn't make sense. We are not testing your understanding to this unit. We are testing your understanding to a geometry thing. I don't want to do that. So in the test, we are not going to give such hard thing. But except the part B, other parts will be important. You must understand how to use the given knowledge regarding the joint PDF to determine the marginal ones. And you need to know how to use the marginal PDF of the random variables to calculate like the mean value, the mean vector, the covariance matrix stuff. Okay. Okay, this is question number 1. We are going to move on to the following questions. So do you have any questions left regarding the question number 1? So if you don't, we are going to move on, okay? Okay. Let's focusing on, because we have only, I think, 40 minutes left, so we need to speed up a little bit. For the question number 2, so I just want to give you some quick instructions so that if you understand how to do that, then I will not do calculation in class. We don't have such time. You can try it out by yourself and verify your works by comparing with my solutions. Okay. So in the question number 2, first of all, we are introducing you a new formula. This formula was not given in our lecture slides, but it was given in the textbook. Because in this practical class, again, which is compulsory, we are introducing this formula. So this formula may be accessible. So you need to know it, but you do not need to memorize this thing because you have your solutions in the test. We have the open book test. You can refer to this formula if necessary, but please bear that in mind. You need to understand this formula now, okay? So this question is about determining the PDF of the y vector of run variable based on the known condition of the another vector of run variable, which is called x. The relationship between the y vector and the x vector is y equal to a by x. We mentioned in the lecture, a is the transformation matrix. Okay, so y vector can be derived by using the a matrix multiple the x vector. And if this relationship is true, so the PDF of the y vector is equal to such kind of thing. This is not hard, so formula is given, so just use it. But if you want to use this formula, you must understand two things. One, what's A inverse? A is the linear transformation matrix, so the inverse of it will be used here. At bottom of fraction, so what that? This is a determinant of the matrix A. In the test, just in case you have such question, you need to be able to manually calculate A inverse and the determinant of the A. So how to do that is a small issue. Okay. Now let's have a look at the question. Okay. By the way, this is for question number 2. Okay. So let's have a question 2. We consider a vector of the variable. We call that as x. So x equal to x1, x2, x3. And we have already been given the joint PDF, so fx. So these just two conditions we have. Now in part A, so please find the joint PDF of, okay, we got a group of new random variables called u, v, w. This u and v and w, these three random variables are in terms of the x1, x2, x3. So what we are going to do regarding the question number 2 is, let me find some space. Okay, question number 2. So now we know the x vector is x1, x2, x3. And we know u equal to x1, v equal to, let me check, v equal to x1 plus x2, w equal to x1 plus x2 plus x3. Now, I want to organize another new vector of random variables, which consists of u, v, w in it, so that I can use the formulas introduced before. Okay, but how to do that? So here, first of all, let's focus on w random variable. W equal to 1 by x1 plus 1 by x2 plus 1 by x3. Similarly, the v random variable equal to 1 by x1, 1 by x2 plus 0 by x3. Finally, for that u random variable, that's equal to 1x1 plus 0x2 plus 0x3. Now, you can see on the left-hand side, we can organize UVW in a column vector. This equal to, on the right-hand side, for each of the UVW, it's just a linear combination of the x random variables. So we got, so let's just extract the x1, x2, x3 out. And then in the transformation matrix in front of the x vector, we just got 1, 0, 0, 1, 1, 0, 1, 1, 1. So all these ones and zeros are just coefficients in front of the x1, x2, x3 in these three equations. So by doing this simple transformation, we are producing the relationship between this new vector z equal to uvw column vector. We derive this relationship between z in terms of our original variable. If you call this as a, this is the x vector, of course. So such relationship is z equal to a by x. Okay, that's that. And the question is asking, what is the joint PDF of the u, v, and w? But because I have put the u, v, w into this vector, so finding the joint PDF of the u, v, w is actually finding the joint PDF of the z vector. Okay, this is how it. But how to do that? Of course, using our formula, right? So formula, Where that? Where's the question? Okay. Of course, using our formula given here, this is the joint PDF of y equals some joint PDF of the other thing. So we use this formula because in this part, in our work, we need to determine what is joint PDF of z. Where is that? Lost it. Okay. That is equal to, so I just copy the formula. It's equal to the joint PDF of the x vector, then A inverse by z divided by the determinant of the transformation matrix A. Okay, get that. For the z on the right hand side, we don't need to consider it because the z is a parameter. Okay, this is done. And for the fx, this joint PDF of the x, we don't need to worry about that because in the question, the condition is saying you are given this joint PDF of the x vector. So we know that the only issue which need to be solved is just this thing and this thing. Okay, and in this question, as we discussed, we know that A is equal to, quickly, so A, so I'm copying this thing from here, okay, is equal to 1, 0, 0, 1, 1, 0, 1, 1, 1. If you have a computer, you can work out the inverse of it, you can work out the determinant of it quickly. But the question is, in the test and exam, you don't have a computer. So how can you work out the inverse and the determinant of it quickly? There are many ways, but I can show you just one quickly, okay? For example, I want to determine what is the inverse of A. So what I'm going to do is, I will put the A matrix 1, 1, 1, 0, 1, 1, 0, 0, 1 at the beginning of a new matrix. And then I'm going to separate it with another identity matrix. For that identity matrix, its dimension is same as A. So we got 1, 1, 1, all zeros of diagonal. And then what we are going to do is just linear transformation row by row in this big matrix until the front part of the new matrix becomes identity matrix. And in the meantime, the later part will be the corresponding A inverse. Okay, so let's do that very quick. So it should be very easy. So let's define the rows. So this is row 1, this is row 2, and this is row 3. So the first row doesn't need to be changed because that is the format. I mean, this part is format of the identity matrix first row. So we keep that unchanged. So 1, 0, 0. Copy the remaining part 1, 0, 0. So they are not changing at all. But for the second row here, we want that to be format of the identity matrix. So the second element should be 1. So this is good. But the first element should not be 1. It should be 0. So now what I'm going to do is to use the row 2 minus row 1. So using this row to minus this row. After this step, so 1, 1, 0 minus 1, 0, 0 give us 0, 1, 0. This is perfect format for the second row of the identity matrix. And then on the right hand side, keep doing the same thing. 0, 1, 0 minus 1, 0, 0 give you the 0 minus 1, negative 1. 1 minus 0 is 1. 0 minus 0 is 0. Keep going. For the third row, we want that to be, so at front, should be 0, 0, 1. But the first two elements are 1s. So I'm going to use the third row minus the second row. So result give us 0, 0, 1. So perfect format for identity matrix. For the later part, will be 0 minus 0 is 0. 0 minus 1, negative 1. 1 minus 0 is 1. Now, the front part has already been the identity matrix. Then, the later half is our inverse of A. Okay, so this is a quick way to calculate the inverse of the matrix, which is 1, 0, 0, negative 1, 1, 0, 0, negative 1, 1. Okay, so that's easy. And the other one is the determinant of the A. For this part, we need to convert the matrix A to the determinant of it and calculate the value. So that give us, so we just put the elements of matrix A into this determinant. That give us so much. 1, 0, 0, 1, 1, 0, 1, 1, 1, just like this. And for this part, I think the calculation should be okay for you. I think you learned this thing from your high school. So this gives us the first element, 1, multiple 1, 0, 1, 1. So this 1, 0, 1, 1 comes from here. And then I think it should be minus the second top element, which is 0, multiple these two columns, which is 1, 0, 1, 1. Okay, and keep going. The third element, plus 0, multiple, and this small square, 1, 1, 1, 1. And then 0 by anything is 0. 0 by anything is 0. That's equal to 1 multiple, 1 by 1, minus 0 by 1. So this is 0. 1 by 1 is 1. 1 by 1 is 1. So result is 1. Okay, so this is a determinant calculation. You need some practice. So for this question, if you have time after class, I hope you can try it out. But I think just that. Okay, after you determine the inverse of A, after you determine the determinant of A, put this one back into the formula we provided in the tutor sheet. You should be able to solve the question without any problem. Okay, guys, I know I am a little bit rushing, but I think this explanation should be sufficient. Okay, and for the remaining part B and part C, very simple. So please try them out by yourself. Again, my solution should be able to give you the details of it. Okay. Let me quick take. Okay, this is question number 2. Any questions? So what's time now? 10 past 10. Okay, let's keep going. There are a lot of questions left. So let x equal to x1, x2, x3, x4. So this is just another vector. So in this vector, so all the random variables have equal mean. The mean values of the x1, x2, x3, x4 are equal. And these 4 random variables are independent. The variance of these 4 random variables are unit. In other words, equal to 1. Okay. So please find the mean vector, covariance, and course covariance matrix of y equal to a by x, where the a equal to the 2 cases, so part A, part B. Okay, this whole thing. And for this question, first of all, having such big A matrix in the test will not be practical, because I can't expect you to finish the manual calculation of a 4 by 4 matrix. That's too hard for you. But 2 by 2 or 3 by 3 may be possible. Okay, so we may have such question or similar. Okay, but will not be so complicated. So in other words, I'm not going to give you a huge calculation workload. So we need to reduce it. But for this question, we just need to understand how to do it. Okay, and I need some space to write this thing. Okay, how about here? Question number 3. So let's focus on the A here. For the A, the the transition matrix A is 1, 1 over 2, 1 over 4, 1 over 8. And then 0, 1, 1 over 2, 1 over 4, 0, 0, 0, 0, 1, 0, and a half, and a 1. Okay, this is A here. And we know y equal to ax. And we also know the x is the x1, x2, x3, x4, the group of vector, the group of random variables. And the question is asking us to determine what is the mean vector of y. So let's just do it. Okay, everyone, could you please try this question by yourself? And let me just drink some water. I have been speaking for 1 hour, more than 1 hour. Okay, just give me 1 second, please. Okay, now let's have a look at how to solve the mean vector of the y. So we want to give the mean vector of the y as the mu y. Mu y. So based on the formula again, we learned from lecture that should be the A matrix multiple the mu x. So I really just want to quickly go through this thing, but I don't want to copy so many things. A matrix is from here, so I just copy here and borrow the values, so I don't need to write down them again. And mu x, based on the condition of the question here, so all the random variables in the vector x have the same mean. So far, we don't know the value of it, but based on the question, so we can assume the value of the mean of the x variables are all, let's say, you can say mu, okay? It's mu, mu x is a little bit tricky. So this mu x, this vector, of course, this is a vector. But inside of this vector, we got the values. So guys, let's just don't use mu anymore for this question. I don't want to just get confusion because that is m. It's just a value, right? M. They're all the same for all four random variables in the vector, right? And then when you just work out this in here, so you need to give us the final result, of course. But regarding this A matrix, so we have some 0 elements. And when you use A multiple this m thing here, so you are going to use the first row to multiple this column to generate a single value here, right? So this matrix calculation. So this first element in this mu y is actually equal to, quickly I just write it for you, is 1 multiple the first m, so 1 by m plus half by the second m, so half m plus a quarter by m plus 1/8 by m. Okay, this is the first element in this mu y vector. For the second element, do the same thing, but this time we are going to use the second row of the A multiple the mu x vector. So I don't really want to just copy them again. So simple for you, okay? And after you finish the calculation, you will get 4 row by 1 column mean value vector for the vector y. Okay, from solution you can find the answer easily, so I skip that. Okay, should be pretty simple. So I finished this mu y calculation. I leave the remaining thing to you. Okay, next one. Anything else we want to determine? Okay, what is the course covariance, right? Let me check. Course covariance, yes. Course covariance, I don't have space. Still in the question number 3, right? So course covariance is a C matrix. This is not single value, right? It should be the bold-faced function C, right? C between x and y. Why we call that as course? Because it involves 2 vectors. One is x vector, one is vector. And in our lecture mentioned, such course covariance is equal to the covariance of the x vector multiple the transpose of the A matrix. The transpose of the A matrix should be pretty simple. Just rows becomes columns 1 by 1, and then I leave that to you. So AT should be easy. The question is, what's CX? CX is the covariance matrix for X. And please notice the term I call this is the covariance matrix of X vector. I didn't mention the course covariance, because if you say course covariance, 2 vectors must be involved. But on the right-hand side, we are going to focus on the vector x only. So I call that as the covariance matrix of x. And this should be, because there are 4 random variables, x1, x2, x3, x4 in this vector x. So this CX matrix should be a 4 by 4 matrix. As we mentioned in the previous question, for such covariance matrix of the vector x, the elements along diagonal direction should be the variance of individual random variables in the vector. But in the condition of this question, you can check it on your side. The question is saying we got unity variance for the 4 random variables in the vector. Unity means 1. So that means for x1, x2, x3, x4, the variables are all 1s. So we can just write down 1, 1, 1, 1 along the diagonal direction. Okay, we have done reasoning in the previous question and also in lectures. So make sure you understand this. Okay, and all other elements of the diagonal direction should be the covariance between any two random variables from vector, and these two random variables are not equal. But this question is also saying, I think, all the random variables given in the x vector are independent. We know if two random variables are independent, they must be uncorrelated. Uncorrelated means no linear relationship. If they have no linear relationship, the covariance of them will be all zeros, right? So R1, this is just a little bit tricky. Could you please quickly let me know, do you understand this or not? Could you give me the message on Microsoft Teams, please? Yes, good. Others? So R1, yes, Stephen, good. Attitude, good. Understood, good. Only you three. How about the others? I don't know. So how many students are here? Oh, really a lot. So others, can you hear me? Are you still with me? Okay. So okay. If you understand this thing, it's good because this is important. Okay, good. Okay, fine. Okay, thank you guys. So let's move back to our class. Okay, now Cx is okay. We are so lucky in this question. This covariance matrix of X give us identity matrix. So if you are using an identity matrix multiple whatever you have, then you just got whatever. Okay, so in this case here, using this Cx, which is the identity matrix, multiple the A transpose, we just got the A transpose. This A transpose is this coarse covariance matrix between the X and the Y, the two vectors. Okay, this is question number 3, the coarse covariance. Anything else? Oh, one more thing. Okay, keep going. What's the next thing? The question is also asking us to determine the covariance matrix of the Y itself. This time, not coarse covariance. It's just covariance of the Y itself. So how to calculate this one? In class, we said this is equal to A transition matrix by Cx by A transpose. Okay, so this is in here. And I really don't think I need to go through it. It should be very simple. So Cx, we have known this is the identity matrix. So A by I by A transpose. But the A by identity matrix is just the A by A transpose. And you know the A, you can work out A transpose. So of course, it will take some calculation, but should be easy for you. So I leave this to you, R1. Is that okay? Should be fine, okay? And okay, this part is done. Regarding the final numerical answers, please check the solutions and select the answers of the tutor questions by yourself. Thank you very much, everyone. Quick look. Okay, everyone. The time for now is 10:22, so we have about 20 minutes left. I want to skip the question number 4. And let's have a look at question number 5, please. Okay, question number 4 should be simple. Okay. Question number 5, go down. Yep, here. Sorry. Again, we got the vector x, which consists of x1 and x2. And okay, guys, you can see in this question here, the covariance matrix is denoted by K. So as mentioned, this is using the old style notations. In our works in this unit, we are changing to using a new style of notations. So this is indicating that Cx is actually equal to such matrix. Okay, And please find the eigenvalues and the eigenvectors of kx. Okay, in our lecture this week, I spent a long time, about half an hour, to go through this one. Okay, so yes, you have to understand how to calculate the eigenvalues and the eigenvectors for a given matrix. Okay, now let's have a look here how to do this question. And again, let's find some. Okay, this good space, not good. Just 1 second, please. Okay, let's start from here. This is question number 5, and we have been given. Okay, guys, I'm using new notation. Okay, so the Cx, so this is covariance matrix of the x vector is equal to. So based on the condition, we got 1, 1, 1 over 4, 1 over 4. So I'm going to work on this question, but before that, everyone, might ask you another separate question. You know, in this x vector, we have 2 random variables, x1 and x2. By observing this covariance matrix of the x vector, are x1 and x2 dependent or independent? Please type your answers in the message. Just let me know. Are x1 and x2 dependent or independent? Dependent. Yeah. So all of you guys got the correct answer. Dependent, that's right. Okay, one more question. This is right, okay? So I will tell you the reason. So x1, x2 are dependent. That's right. The second question is, are x1 and x2 correlated or uncorrelated? Again, by observing that the covariance matrix of the x vector are x1 and x2, these 2 variables in the x vector, correlated or uncorrelated. Okay, 2, 3 correlated. Guys, you are all correct. Okay, they are correlated and dependent. Okay, why? The key thing is given here, 1 over 4, 1 over 4. These 2 elements are of the diagonal direction. So you guys did a good job. Very nice. Okay. These 2 elements, 1 over 4, 1 over 4, are of the diagonal direction. They are corresponding to C x1, x2 value, or C x2, x1. The same thing. That matter. The order is okay, right? This matrix is symmetric anyway. These are calculating the covariance between these 2 variables, and their values are greater than 0. In other words, non-zero. If you got non-zero value for the covariance, this means these 2 variables, x1 and x2, must have linear relationship. So they are correlated. So you guys did a good job. If they are correlated, they must be dependent. Okay? So no problem at all. Very nice. Okay, so for this question, so we go back to our question, right? And let's have a look at how to solve that. We want to determine the eigenvalue and the eigenvector based on this matrix. So the first thing is to determine the eigenvalues. So we need to construct, so Cx minus the lambda by the identity matrix I. This lambda is actually the eigenvalues we want, okay? I don't want to explain the reasons of this approach. So from your year 1 math unit, you should have already learned it. So we just use it today, okay? This gives us, we just copy 1, 1, 1 over 4, 1 over 4. This is our Cx multiple lambda. It's just a value later along. And for the identity matrix, the dimension should be same as Cx. So 1, 1, 0, 0. So this gives us, put lambda into this identity matrix. So lambda is gone and go into this eigenmatrix. Using matrix A minus matrix B, so just element by element subtraction. So 1 minus lambda, 1 over 4, so 1 over 4, 1 minus lambda. So this is a new matrix. And then we need to find the determinant of this new matrix. 1 minus lambda, 1 over 4, 1 over 4, 1 minus lambda. We want to determine this. This thing gave us, actually, again, 1 minus lambda, 1 over 4, 1 over 4, 1 minus lambda, this whole thing. But this is not matrix anymore. This is determinant of it. So this gives us a so-called value or a function because lambda has not been known yet. So this gives us 1 minus lambda by 1 minus lambda. So the product of the two items minus the product of the other two elements. So 1 over 4 square. So for determining the value of the lambda, so we need to set this thing to be 0. This gives us 1 minus lambda square equal to 1 over 4 square. So square root both sides give us 1 minus lambda equal to 1 over 4. But we have two possible values, positive and negative. So that means the lambda value will be equal to 1 minus positive or negative 1 over 4. In other words, lambda could be lambda 1 equal to, let's see how much? Maybe 1 minus positive 1 over 4. So give you 3 over 4. Lambda 2 is 1 minus negative 1 over 4. So that give you how much? 5 over 4. These two are the eigenvalues. And for each of these two eigenvalues, you can find one corresponding eigenvector. Again, everyone, before we move on, I want to ask another question, which we introduced in our lecture. Now, by observing these two eigenvalues, could you tell me, can this Cx or the X, this stuff, can that be diagonalized? Please give me your answer on Microsoft Teams. Again, by observing the values of the eigenvalue of the matrix, can this Cx be diagonalized or not? Please give me your response, yes or no. Even, yes. David, yes. 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 Okay, good job, Atish. Yes, you guys' answer is right. Why? Okay, because you have unique eigenvalues. These two values are not equal. 3 over 4 and 5 over 4 are not the same. They are not identical. And the dimension of this Cx is 2 by 2. That means if you got 2 by 2, okay, sorry, leave that alone. If you have n by n matrix, if you want to judge if this n by n matrix can be diagonalized or not, the condition is you must have n unique eigenvalues. But for this question, we said it's 2 by 2 Cx matrix, right? And we have two unique, not same eigenvalues. Then this Cx can be diagonalized. Okay, good work, guys. Okay, this step is done. We know the eigenvalues, but how to use the eigenvalues to determine the eigenvectors? So you have to do that step by step, one by one. So now let's assume the lambda 1 equal to 3 over 4. So we want to find out what is the corresponding eigenvector P1 when the lambda 1 equal to 3 over 4. So the formula calculating this thing is by using the feature of the eigenvalue and the eigenvector. So using Cx, the original 2 by 2 matrix, multiple this eigenvector is equal to the lambda 1 by P1. Okay, this is again year 1 or year 2 math unit knowledge. Maybe you have already forgotten it, but this can help you to record this. Okay, and the next step, put all the conditions in. So Cx is how much? 1 over 4, 1 over 4. But for P1, sorry, I don't know the value, right? So we need to construct this vector. Sorry. So let's just give this P1 vector the particular elements inside, okay? Equal to this one. That's equal to lambda 1 has been known. It's 3 over 4, right? And then copy it again. So equal to P11, P12. Now this is so easy, right? On the left-hand side, we are going to use the first row to multiply this column, which is equal to this number multiple the first element in this P1 vector, right? So this gives us 1 by P11 plus 1 over 4 by P12 equals 3 over 4 by P11. This is the first equation. The second one is the same procedure, but for the second row of this CX matrix. So that gives us 1 over 4 P11 plus 1 by P12 equals 3 over 4 P12. Okay, we derive these two equations from this matrix calculation and simplify it. In the first equation, P11, P11, we just group them together. That gives us 1 over 4 P11 plus 1 over 4 P12 equals 0. In the second equation, P12, P12 common terms combined together. 1 over 4 P11 plus 1 over 4 P12 equals 0. Oops. We got two identical equations. But no matter which one you use, okay, we can cancel 1 over 4 on both sides, right? So these two will give us one single equation. So not R, is P. P11 plus P12 equals 0. In other words, even though you have two equations, you can't know the exact value of the P11, P12 from them because these two are merging together into one relationship like this. From this relationship, we just know one thing, P11 equal to negative P12. Is that enough? P11 is the first element, P12 is the second element. So if you put these two back into the P1 vector, so P1, if it looks like P11, negative P11. Or if you want to write negative P12, P12. Yes, this relationship is correct, but it's not good enough because I want to know the numbers, the numerical values, not just notations. But how to derive the values of the P11, P12? Okay, in the lecture I mentioned, all the eigenvectors must be normalized. What does it mean? That means the magnitude of the eigenvector must be unity, is 1. So in this case here, actually, because you have only two elements, right? The magnitude of the P1, this eigenvector, is equal to square root the summation of the square of individual elements inside. Because you have two elements, right? P11 square plus P12 square. If you have more elements, so keep plussing the square of the elements of this vector. But for this question, 2 will be sufficient. So this thing will be equal to 1. So this process is called normalization or normalized vector, the unit size. Okay. I think this is easier. P11 square plus P12 square equal to 1. But we have already known this relationship. So P11 equal to negative P12. So this gives us negative P12 square plus P12 square equal to 1. Negative sign is cancelled. And this gives you P12 equal to square root 1 over 2. So which is square root over 2. And P11 equal to negative P12 is negative square root 2 over 2. Okay, now we got numerical values. By putting these two values into the vector, so we got P1 equal to negative square root 2 over 2 or square root 2 over 2. Not or, I mean and. Okay. Okay, this is the P1. The first eigenvector, which corresponding to lambda 1 equal to how much? 3 over 4. For the second one, so when the lambda 2 equal to how much? 5 over 4, right? Do the same thing, the whole procedure. By the end, you can find the P2 is equal to, so I don't do calculation, I just give the answer. It's 1 over square root 2. Or if you want me to write down same format, so let's give you square root 2 over 2 and square root 2 over 2, the two identical elements inside. for lambda 2 equal to 5/4. So for this part, they just do that by yourself. Should be easy. Okay. Okay, now we have done the majority of work. But can you recall at the beginning I asked, can CX be diagonalized? Your answer were correct. Yes, it can be. But by how? By using the P matrix. What's P matrix? P matrix is the collection of the eigen vectors. So this will give you P1 vector and the P2 vectors here. P1 vector, negative square root 2 over 2 and square root 2 over 2. So these two elements are coming from the P1 vector. And then the next row is about square root 2 over 2, square root 2 over 2. So these two, highlighted. These two vectors, two values are coming from the P2 vector. Okay, so this is just how to organize the P matrix. But how this P matrix can be used? This will be linked to our transformation. Okay. So, because of what we want to do in this question is we want to diagonalize the CX matrix. So after diagonalization, we produce this thing, which is equal to A by CX by A transpose. But by using this matrix P here, this is actually equal to P inverse by CX by P. But in this question, we know because CX is a symmetric matrix, so P inverse is actually equal to P transpose, and then CX by P. This P is the matrix we produce here. And okay, this is what happened. But after you finish such diagonalization, what will be the result of this diagonalized matrix? This will be equal to a 2 by 2 matrix, of course, because it has already been diagonalized. So the off-diagonal elements will be zeros. But along this diagonal direction, its value is just 2 eigenvalues, 3 or 4, 5 or 4. Is that right? Yeah, that's right. Okay, this is the whole process. And for the question number 5, I think the calculation should be fine, not easy, but not hard. Sorry, it should be okay. But there are some important key steps you need to understand, and also for some matrix calculations, you need to know how to do it manually. But the whole question is not as hard as the question number 1. Okay, everyone. The time now is 10:40, and I think it's time for us to finish this practical class, and I'm stopping the recording now.